Today I decided to go to high technology. Okay, so we will see how it works. Okay, so let me first quickly review what I said last time, or somehow just one aspect of that. So we replaced Ising model configuration by its contours. We had weight contours, and actually weight of contours, which was e2 minus 2 beta, e2 minus 2 beta times length of the contour. And we got this expansion here, or not expansion, I should say, I mean, the word expansion here should be replaced by representation, maybe. So this is something I would call low temperature representation. So my full partition function, or real partition function, or physical partition function at zero external field with plus boundary condition is up to some constant sitting in front of it, is sum over collections of contours. There should be product here, product over gamma in gamma, e2 minus 2 beta gamma.
Can you write on this transparency?
This is okay. So it is sum over gamma, product over small gamma in gamma, e2 minus 2 beta gamma. Okay, so you see high technology and it's wrong from the very beginning. Okay, so first I would like to show you, because this will be, what is written here in red, instead of excluding this error, that should be this product. So what is written there?
So next one is product or summation?
This is correct, this is wrong. Yeah, sum should be product, okay? So let me see, we will see whether I have it correctly in the other part. So this is somehow example of low temperature representation. Now I would like to quickly show you what would be high temperature representation, which have final formula, again in red, will have similar structure as this one. Okay, so what do we do very quickly? So we take our, this time I take free boundary conditions, so it's partition function in volume lambda with free boundary conditions, and I take even non-zero h. Okay, so I have sum over sigma lambda. Similarly as Alan in preceding talk, I replace e2 sum by product of e2 something. Okay, so I have product over nearest neighbors ij, e2 beta sigma I sigma j, and then I have product over all i's in my volume lambda, e2 beta h sigma I. Okay, so this was just the original Ising Hamiltonian. Okay, now I use the simple identity. I replace this e2 beta, the sigma I times sigma j takes only two values, plus and minus 1. So it's easy to show that e2 beta and either plus or minus 1 equals cosine hyperbolicus of beta plus this plus or minus times sinh of beta. Okay, you agree with this formula? I am going to use the same formula also here. Okay, now I am going to take out cosh hyperbolicus beta and cosh hyperbolicus beta h, so I will take it out of all my expression, and what I will get at the end is this thing. So I have this cosh hyperbolicus beta to the number of edges in my volume times cosh hyperbolicus beta, or cosh beta h, I don't know how to pronounce it, cosh beta h to my volume, and then I have sum over all configuration, product over ij, 1 plus sigma I sigma j tanh of beta, product over I, 1 plus sigma I tanh of beta h. Okay? So what I do next is the following thing. I will somehow express these products here, I expand it. So simply I have, sometimes I take ones, and sometimes I take these edges from here. And similarly here, sometimes I take one, sometimes I take these vertices. So these two products can be rewritten as sum over pair of objects. Gamma is collection of edges, and V is collection of vertices. Okay, maybe let me show you a picture of this. So I have some collection of edges, okay, and on top of that I have collection of vertices of my lattice. Okay, and then I take tangent, then I take tanh hyperbolicus beta to the power number of the edges in my collection of edges, tanh hyperbolicus beta h, number of the vertices in my collection of vertices. So V are these red crosses here. And then what remains is product over all edges from gamma, sigma I, sigma j, and product over all i's from my set of vertices, sigma I. Okay? So now I would like to with fixed gamma and v, simply to interchange these two sums. So with fixed gamma and v to produce the sum over sigma lambda. Okay, so I am gamma and v are fixed, so I go through that and I sum this with fixed gamma and fixed v over all sigmas. Okay, and it's easy to realize that whenever I will have, there is a product of sigma I, sigma j's here against some sigmas. How many times, if I look on a particle vertex, how many times sigma will occur? If this vertex is even degree in this graph, then this corresponding sigma will occur even number of times, and there will be +1 there. If the vertex is odd, like this one, or maybe this one, okay, then the sigma will occur 3 times, or 1 time here, and I have this particular sigma. Now I am summing over all sigmas. So whatever will be the rest summing over the remaining sigmas, this one sigma will occur with plus and minus, and I will have the same contribution once with plus and once with minus, and it will disappear. So for example, this particular graph will not contribute because there is a lot of vertices that are odd here somehow. By odd, I mean either odd vertex of my graph, or if I include this cross, so here I have, it is even vertex of my graph, but including this additional cross, it contributes sigma I to the power 3, and this is sigma I, which has this plus minus symmetry. So the only graphs that will somehow, this is wrong. Why I did this? This shouldn't be here. These two crosses shouldn't be here. And oh, sorry. This is the correct thing. So the only picture that can contribute, non-zero contribution is something like that, where I have arbitrary graph, but whenever I see odd vertex of my graph, then I have to place a cross on it. Okay? So in other sense, I can sum just over gammas that are graphs like that without the crosses, and I have simply tangents hyperbolicus beta to the number of edges times tangents hyperbolicus beta h to the number of odd vertices of this graph. Okay? So I have this thing, which is somehow written here, the sum over sigma lambda. Whenever I have such a graph, then it is simply 2 to lambda. Whenever I have other graphs like that, then I have 0. Okay? So if I summarize all that, what I'm getting is my partition function with 3 boundary conditions. There are some prefactors, this cosh hyperbolicus of beta and of beta h. Then there is this 2 to lambda, and then I have sum over gammas. Now I can forget about v's because gammas are my graphs that have even or odd vertices, and simply in odd vertices I have to supply this tanh beta h. Okay? But look, this is the similar formula as what I had before. I have sum of collections of some objects, product over connected components of these objects, okay, and some weight factor. Here the weight factor was E2 minus 2 beta times gamma. Here the weight factor is all this animal here. Okay? But otherwise it looks very, very similar. Okay? So this is somehow, this is in general something we will encounter, or we encounter quite often in statistical physics, that we have, this is exactly what you called, how did you call it? Stable set enumerator somehow. Okay? So this can be interpreted as stable set enumerator if I define correctly my graph, which I will do soon. But in any case, the structure is something like that. I have sum over collection of some geometrical objects that are disjoint. Then I have product over the objects in this set of objects, and I have some weight factors of these objects somehow. Okay? We call, so we call these objects usually polymers, so in abstract sense somehow. So I have each polymer has some weight, and I have sum over collection of polymers, product over polymers in this. And notice there is no interaction between, somehow there is interaction between disjoint polymers just in the fact that they shouldn't intersect. There are disjoint. But otherwise, when they do not intersect, there is no interaction. Whether I place two polymers here, or here, or here, their weight is exactly the same. Okay? So in both my partition functions at low temperature, I had this partition function with the factor e to minus 2 beta gamma. At high temperature, notice that at high temperature, beta is very small, and this tanh is very small. So at high temperature, I have these weights that are again small. So either at high temperature, this expression, or at low temperature, this expression, both of them look like that. And both these can be abstractly described. So we are somehow interested now, as Alan stressed, in the limit of 1 over lambda logarithm of such a partition function. Okay, this is our goal, to understand how this thing can be obtained. Okay, so in particular, we are interested in logarithms of such objects, how to deal with them, what we can show about them, and in particular, we are not interested so much in how do you call it, formal series. We are interested in real convergence of the objects like that. For which weight W, logarithm of Z is well defined, or this limit is well defined and it has good properties. Okay. So now I'm starting to describe everything in pretty abstract sense. Namely, I am going to replace my polymers, my geometrical objects. I will consider a graph, and these will be vertices of my graph. So I have an abstract graph. Okay, the vertices of these graphs are my gammas, and two vertices are connected whenever the corresponding gammas, if I have contour like that and contour like that, they intersect, then corresponding vertices will be connected. Okay. So notice that this graph is huge because the number of distinct contours is infinite. It's countable. Okay. So I have huge number of contours, and even a single contour has infinitely many other contours that intersect it. Okay, so degree of every vertex is infinite also. So it's a huge graph. Okay.
When you see that two contours intersect, you allow them to intersect in just one point?
No, they can, as I draw, they intersect in a lot of points. Whenever they intersect, pardon? Yeah, whenever they intersect, I say they are connected by an edge in the corresponding graph. Okay, so this is my abstract graph.
But you don't have to work with an infinite polymer graph.
But I want to work with an infinite.
Because you're in a finite volume lambda, so there's a finite but huge number of contours, and all you so.
But I am interested in also somehow evaluating, for example, writing explicit formula for the free energy, and this will contain all polymers of all lengths somehow. Okay. So this is my graph. So vertices of my graph are polymers, and edges are connecting those polymers that intersect. Okay? Now, given this graph, so the vertices I call abstract polymers or something like that, and two vertices form an edge whenever they are incompatible. I mean, I can even, in some situations, intersection is too strict. I can also sometimes, when there is some interaction between contours, maybe if they come to the distance 10, they are already somehow, they feel each other, so then I consider them incompatible, and this will somehow aggregate of these two contours that are somehow at such a close distance, I consider to be one big contour. So somehow this incompatibility can be extended a bit, not really just disjointness, okay? Now I suppose I have some weights on these vertices, and the weights I suppose are complex numbers. Okay, it's, as Alan's explained us, it's often useful to extend our variables to complex numbers. And now if I take, and this is important step somehow in all these considerations, is, somehow I am interested in partition functions in certain volumes. So I take a volume, and now I will have all possible contours living in this volume. Okay, So which is certain set of contours, let me call it L of the volume lambda. This is set of contours living in volume lambda, okay? So I could have restricted to those contours and work only with collections, finite collections of contours that are living in a given volume. But then it would be somehow difficult to do the proofs. And what was somehow important step in understanding how to work with this thing was to take, any finite subset of contours and define all the objects just for finite setups of contours without, any connection with volume or anything like that. So for any finite L, I can define, how did you call it again? Stable set enumerator. So I can define my partition function ZL of W, which is sum over independent sets. This L is subset of vertices, so I have induced graph on them. Okay, so I simply sum over independent sets in L. I have product over vertices in I, W, V, which is exactly the same thing I have here. Okay. Okay. Of course, in this sum, I can also have a term where I is empty. So for I empty, I take the contribution to be 1. It starts with the 1, this sum. Because this corresponds in my Ising model. If I have no contour at all, I have this ground state contribution, which somehow up to this constants that were in front of everything is giving me 1.
Excuse me, do you mean I must be proper subset of L?
Well,
I has to be an
if L,
independent subset.
no, not proper subset.
No, independent. or
Independent.
Yeah, independent. Is it possible I equal to L?
If you choose L to be independent, then
So you,
The question is, what is the meaning of that subset symbol? Is it proper subset or not?
it is subset of L.
Not proper subsets.
What is not proper? Proper is that it differs from L.
Yes.
If L, I is independent set. If L happens to be independent set,
usually
then among those there is also I equals L.
usually we use this sign as a proper subset.
No, so I am not.
The keyword that you didn't write.
So sorry, but this is, in set theory you use this.
No.
Yeah? No? Really?
Most people want
Only
to
an
include
analysis.
L as a possible.
Okay, analysis. I am, in contradiction what Alan is saying. I do not believe that statistical physics is
Okay,
part
that's
of
fine.
probability. It is part of probability union with analysis. You have complex variables here, so somehow. Yes.
Something escapes my mind here because you are saying that two contours, which are now vertices,
Yeah?
are incompatible because they overlap, and then you connect them, and then what does it mean?
No, I do not connect them. I compute. This was just the story. What I mean incompatible. This was just
Draw
some.
an edge between them.
Yeah. So forget about what I said before. Incompatible means intersecting, not disjoint. Yeah.
No, this
Yeah.
edge.
I was just saying that you can extend the notion of incompatibility to a more general setting, but somehow for us incompatible means not disjoint.
But
Yeah.
previously the contours were disjoint, and those contours and
There is no edge between them, and they are independent. They contribute to my independent sets then. Yeah. Because here in this sum, I am summing over gammas that are disjoint. There are a collection of disjoint gammas. So this is independent set in this terminology. And then I have product over the elements from this independent set and corresponding weight.
So each independent set, I, corresponds to a pairwise mutually compatible
Compatible.
collection
Yeah.
of...
This is definition of independent sets. Yeah.
vertices,
Yeah.
not of edges.
Pardon?
Okay.
I is subset of vertices. L is subset of
Of the
vertices.
polymer graph.
Yeah.
No, not edges.
Okay. Now I have so now I would like to think, so I have fixed finite L at this moment. So my W's take values in C to number of elements in L. Okay, so this huge complex space. Okay, so I would like to think about this as a function of this W, as a function of this W in this space. Okay, so in particular, what I know that this is perfectly analytical function. It's just some polynomial. Okay, it's nice analytic function, and moreover, at W equals 0, it is 1 due to this condition here. okay? At w equals 0, only empty set contributes just 1, okay? So I have entire function that is 1 at origin. So certainly there exists, for fixed L, there exists some neighborhood of origin where it is nice analytic. So I can compute Taylor expansion in the origin, okay? And my Taylor...
Of the logarithm.
Pardon?
Of the logarithm.
Of the logarithm. So I can compute, here it's of course polynomial, there's nothing to compute. I can compute Taylor expansion of logarithm, and it's something here, okay? So this is multivariate Taylor expansion. I have this many variables w indexed by v, okay, indexed by this L. And then I have this multi-indices here. You were using alphas for them this morning, yeah? Multi-indices alpha. So I have multi-indices x. This is the set of multi-indices. I have some coefficients, just Taylor coefficients, including something like x factorial here or something like that. And then I have w to x, okay? So is the notation clear to everybody? X is simply a mapping. X is a mapping from L to numbers 0, 1, 2, and so on, okay? And say Wx is product over V in L, Wv to the power xv, okay? Okay, so we have that. This we have free of charge, no work, okay? Now there is a couple of observations about this. So let me write this expansion here for you. Logarithm of ZL of W equals sum over x's in script XL. These are all multi-indices on L. Then I have something I called ALX. Okay, and then I have WX.
Excuse me, I got lost. W, at some moment you said it belongs to C to
Yes.
L. So it is like
So it is this WV.
analytical, right?
Yes,
And then what does it mean then?
exactly this. W to X is product over V in L, W of V, X to V. Yeah? Instead of putting this V as an index here, I put it as variable, but it's somehow. Yeah? Okay, so now a couple of simple observations about these indices, ALX. Okay? So first observation is funny that already here we can claim that ALX doesn't depend on L. Okay? This is somehow easy to realize but more difficult to describe, so somehow I will describe it by my hands.
Provided that L is big enough to include the support of X?
Yes, sure. It doesn't make
Otherwise
ALX.
it'll be zero.
Yeah. So whenever support of X, which is the set of all V's such that XV is bigger than 0, okay? So provided that support of X is subset of L, okay? So what is the reasoning? You simply compute, I have these logarithms at LW, and I compute this coefficient. It is Taylor expansion, so it will be a couple of derivatives with respect to W, and then I put W equals 0 at the end of my computing the derivatives, okay? And you have to realize that somehow, you know, my original, also I should write my original formula for ZL. ZLW is the sum of these i's, product of V in I, W of V, okay? So somehow one should realize, but as I'm saying, it's difficult to describe, but it's clear when you somehow think a bit about that, that somehow those variables that would not appear in the derivatives, that would not appear in support of X, okay? Then if I put them at the end, W equals at this, but if I have a V, a particular small V that doesn't depend, that is not contained in support of X, okay? Then I am not computing derivative with respect to W at this V, okay? And at the end of all my derivations, I am putting W equals 0. So I could have as well put W equals 0 for this V at the very beginning. It would not influence my computation. So as a result, I'm claiming that AL at X is exactly the same what I would get if I replace L by support of X. Yes?
So L is the set of all contours in the infinite volume lattice.
No, L is finite set of contours. You just pick up a couple of contours, okay?
But at this stage, one, I think, does better to forget about contours.
Yeah, forget about contours.
Forget about contours.
These are vertices. Now I'm talking about graphs. So I take finite number of vertices in my graph.
But you still need to allow L to vary, otherwise saying support of X including L is by definition.
So this is what I said here. I mean, there should be proviso there that support of X is subset of L. Then it doesn't depend on L.
No, but you said that you define X as a map from L to 0, 1, 2, etc.
Okay, so I could define, you know, so I was slightly sloppy in my definitions. There is this, you know, XL is exactly what is here. Okay, I could have defined union of all finite L of XL. Okay, and this I would call X. And I will actually use this X later. And X is any finite, X is any collection of, finite collection of, X is multi-index such that sum of XV is finite. Yeah, with finite support. So X is collection of multi-indices with finite supports. I will never use any bigger thing.
Isn't it true that even you can say something even stronger, that it's not that it depends on the support of X, it depends only on the
X.
contours, on X itself.
Yeah.
Who cares what X?
Yeah, exactly. So I can forget about this. I can simply introduce numbers AX, and this is still true. Okay?
Well, A support X of X is obviously depends only on X.
Yeah, exactly. This was, you know, only you can take partition function in the volume support of X, so to say, in support of X, compute this partition function, compute its Taylor coefficients, and this will be my AX. This will be definition of my AX. Okay, next step. AXs are real. So this is somehow just look on this polynomial. The polynomial is nicely real coefficient, so it's true, it's clear that Taylor coefficients will be real numbers. Okay? AX equals 0 whenever whenever the graph restricted to support of X is not connected. Yes? Okay? So it means whenever my support of X, so support of X is couple of vertices, so whenever it splits in two pieces with no connection between them. Because then my partition function will be product of those two. Okay. Now I take logarithms, so I have sum of two logarithms, and now I'm computing derivatives with respect to it with variables from here and here. And always, these depend only on variables from here, and these depend only on variable from here. So always there will be one part that will not be touched, and after putting w equals 0, this will disappear. Okay? So, pardon? Whenever G, so the graph living on support of X. Support of X is subset of V, so is set of vertices. G of support of X is simply some graph. So whenever this graph is not connected, okay? This we call, because if you somehow, for a second, if I come here, how is this, how does it look, this support of this support of X? So I have collection of contours, and they are jointly using my connections, my edges, they are connected in that way. So they form some sort of cluster. And this is the reason why we call all this subject cluster expansion. Okay? So here is some AX in physical language, AX equals 0 whenever support of X is not a cluster. So it's living only on clusters. Okay? I cannot have non-zero contribution to something like that is union of two pieces that are disconnected. Okay? And the final property, which is slightly more difficult, is the following one. AX has this alternating sign property. Okay? So AX has the sign -1 to to the, you know, absolute value of x is sum, absolute value of x is defined as sum over v xv. Okay, this is what I call absolute value of x. Okay, so let me prove this. This will be somehow, this will be essentially first half, so the proof of cluster expansion consists of two pieces. One piece is proving this alternating sign property. Once we will have it, I will formulate really cluster expansion theorem, and then the proof will be very quick. Okay, so lemma. So this is somehow, so there was this alternating sign property. Let me write it once more somewhere here. I'm running out of space on these pieces of blackboards around the screen. Okay, so how it was, -1 to x plus 1 times ax is non-negative. Okay, this is my alternating sign property. I'm claiming that this is the same as this thing here. Okay, that it is equivalent. I'm claiming that this is actually alternating sign property. So what is this lemma? This lemma is saying I take finite L, for every finite L, all coefficients of minus logarithms at L taken with the weights that are minus absolute value of W has only, so if I expand this in powers of W, absolute value of W to the power x, all the coefficients will be non-negative. Okay? So how I can see that this is equivalent to my sign property? Look, I have here this formula for logarithms at L. Okay, this is what I want to expand. But I want to take logarithms at L at the value minus absolute value of V, which will mean that here I also let me do the computation. So I have sum over x's, ax, and then I have minus absolute value of W to the power x. Okay? So if I somehow take out this minus, so this I have -1 to the power x. Okay? And then I add one additional minus, so I have this to power x plus 1. So if ax has exactly the same sign as this, then I will have only positive coefficients in the expansion of this, because this minus is I take minus logarithm, not logarithm. Okay? So it is clear that it is exactly the same as the sign property, and now I'm going to prove it. I'm going to prove it strangely by induction on L. Okay? So let me first, just to simplify my notation, let me denote partition function computed at this minus absolute value W. Let me call it ZL star. Okay? So I have this ZL star. Okay, so by induction I have to start with something. So if L is empty, then simply Z of empty set is 1. So I have Z star equals 1. Logarithm of Z is 0. Minus logarithm of Z is also 0. It has only non-negative coefficients. Okay? If you wish, I can even go farther. So let me take the set consisting of only of one vertex. Okay? Then my Z partition function with one vertex is simply 1 plus W of V, because either I take this set or this vertex or I do not take it. Now this is in the point minus W, absolute value of W, so I take 1 minus absolute value of W of V. Now I take minus logarithm of this, and minus logarithm of 1 minus something has only positive coefficients. We simply know how to expand logarithm. Okay? Okay, so we have beginning of our what is this? Yeah. Yeah, it's correct. You know, I have here on the screen, I am very clever. I have on the screen I have also next step. And now I look on the right hand side somehow, and then I didn't realize I see also the future on my screen. So I know what I'm heading at. So now I suppose that that my finite coefficient property is valid for L, and I extend it by one additional vertex. Okay, so I have this L bar. Okay, now let me compute what is ZL bar star. Okay, so by definition, ZL bar is something similar as this ZL, only you take, instead of W, you take minus absolute value of W. So we have sum over independent sets, product over V in independent sets. Okay. Now, this independent set may or may not be, it is independent set which is subset of L, or of L bar now, okay? So it may or may not be subset of L. So if I collect all those terms that are subset of L, I am getting this, ZL, okay? And the remaining terms, they always contain V, because this is the additional guy who is somehow on top of L bar, which is outside. So there is this minus absolute value of WV. And then I am summing over independent sets that are such that they are consistent with V. So if I don't know whether this is proper graph theoretic notation, but somehow this is actually, I take all independent set in the set L minus neighborhood of V.
The closed neighborhood.
Whatever.
Take out V also.
Yeah, L doesn't contain V, so I do not care. Yeah? Yeah.
Sorry.
So it is L minus n V. So this formula is true. Okay? Okay? So having this formula, I can take logarithm. Okay? I have minus logarithm of ZL bar star equals, so how do you call this? I factorize, I take out ZL star, so I have ZL star times 1 minus W and the ratio of these two guys. Okay? If I apply logarithm of this on this, I have minus logarithm ZL star minus logarithm of this guy here. Okay? Now, this guy, what I want to claim? I want to claim now if I expand this in power of absolute value of W, it will have only positive coefficients. This guy I know has positive coefficients. This is my induction hypothesis. Okay, so it's okay. I'm happy with this term. The other term is minus logarithm 1 minus something. So if I will be able to prove that this other guy has only positive coefficients, then we know that minus logarithm 1 minus x has only positive coefficients, so this positive coefficients on top of positive coefficients coming from the logarithm will give us also positive coefficients, so we just have to look on this thing here, on the ratio here. Okay? And for that, we are going to use our formula. Okay? So I have Z in the volume L minus NV divided by Z in the volume L. I can write for Z in the volume L, so here I have logarithm, so if I exponentiate it, I have ZL equals e to this sum. Okay? This guy equals e to some other sum, and the difference of these two sums gives me exactly this. Okay? Sum over all multi-indices that are in XL, but they are not fully contained in L minus NV.
Is there a minus sign?
Pardon? Because this guy is smaller than this, so there is, somehow I subtract the terms upstairs minus downstairs, so there is additional minus sign. There is a smaller sum here and bigger sum here.
That's why I would have thought.
Yeah. So there is, I have e to smaller sum divided by e to bigger sum, so I have e to minus, and and I want.
There is another minus sign because you're using absolute value.
Because I'm using minus logarithm here. Or what? Yeah, because this is the formula with absolute value of v, but with minus 1 to some power ax. And now I replace this minus 1 to some power ax by absolute value of ax. There was no absolute value of ax here.
The point is that a of x has the sign minus
I am
1.
using this property for the
Yeah,
ax.
minus 1 to the x minus 1.
Yeah.
Right.
Yeah, for those that are living in L, because this I have already proven. Okay? So having that, I'm done. Okay? I am happy also with this term, and my lemma is proved.
So you have done
deletion contraction on the vertices, which means that your natural setup should be on the dual graph, because the deletion contraction is usually on the edges in a natural way, isn't it? Would you agree?
I'm not sure that I understand what you are saying.
Well,
so-
this is deletion contraction. We can see all the structure of deletion contraction.
yeah,
And you're doing that on the vertices, while
yeah.
usually we would do deletion contraction on the edges.
Well, they're different polynomials. I mean, for the Tut-like polynomials, the natural thing is on the edges. For this independent set polynomial, the natural thing is on the vertices.
Yeah, it's simply the
They're
weights are sitting on the
analogous but
vertices.
different.
I don't know how to put it, but you are saying me that I should consider dual graph, and maybe then on the dual, I don't know.
Then naturally you will be working on the edges.
Yeah. I don't know. We can discuss that because somehow actually motivation of all this is somehow to show you this thing in our language, and you will see that it is simple in your language, and it's somehow giving something meaningful for. Okay, so now I am interested in diameter of convergence. Okay, this is my, because up to now I was slightly cheating in this proof here because I was somehow working with this expansion as if they work, but somehow I was working with finite L or finite L bar, so I am always able to suppose that I am in sufficiently small neighborhood that all logarithms at L up to L bar are convergent and everything works.
Well,
Okay?
everything you did so far can be interpreted simply as a statement about formal powers.
Yeah, exactly, about coefficients, yeah. Okay, so but now I really want to prove convergence or diameter of convergence, and for that I will introduce somehow my diameter of convergence. So I have this multivariable, so I have to say I have to state what is the polydisk of my convergence. So here is my polydisk. I simply take some sequence of numbers R defined on V. So I have a mapping from V to R plus, okay? And for every L, I can consider a polydisk, which is a subset of C to L, and which is simply set of all W's such that W at V in absolute value is smaller than this RV. Okay? So this is my polydisk. And now I am looking for a condition on R such that I will be able to claim that this series converges on my polydisk. Okay? So what are the assumptions on R? The assumptions are very strange. They look like that. Okay? The assumptions are slightly unconstructive, but you will see in the proof that they somehow come naturally, exactly in this form. So I suppose that there exists a small r from V to interval 0, 1, including this semi-closed interval, including 0, such that for every V, RV is smaller than small rv times product over neighbors of my point V of 1 minus RV prime. Okay, so this is the condition. Okay, I'm sorry for that. This is the condition. It looks like that. Actually, this condition stems from the condition that was first written by Dobrushin, and the Dobrushin condition was even more horrible. This is already a form that was proposed by Alan and Alexander, I believe.
Well, it really goes back to the analogous thing, the Lovász local lemma is
Yeah,
like this.
exactly. Yeah. Okay, so now we have a theorem. Theorem about cluster expansion. So in this setting, having our condition star, so maybe I should write it somewhere, because this will come out in the proof. So our condition was that RV is more or equal than RV times product over V prime that are neighbors of V, 1 minus RV prime. Okay? So the theorem is saying there exists A, we already know, here we have them, A, from multi-indices in the sense I was somehow defining here as union of all, with finite support, to R, such that if R satisfies the star, here, then the following is true. Then first, for every finite subset of V, finite, and any W from my polydisk, ZL differs from 0. Remember W is complex, so there is no reason why ZL should be. So this is the main obstacle, the zeros somehow. So on this polydisk, with R that satisfies this condition over there, ZL is different from 0. And once it is different from 0, then of course our expansion applies. And we have this formula here, which is rewritten here. Okay? So this is the first statement of cluster expansion. The next statement is something about convergence. Here it is. Sum, and now I am summing, the sum, even this sum is infinite, because I am summing over multi-indices, and these multi-indices, they go up to infinity. So even when the set of contours here is finite, this sum is infinite, okay? But here I have double infinite sum, because I'm summing over all multi-indices in, as large as possible. So there will be contours as big as possible here, okay? Such that support of X contains one particle contour, one particle vertex. So these are, remember that this AX is non-zero only on guys like that, so I simply take one guy, and now I have collection of, as big as possible guys, but they are, they are disconnected pieces, they are these clusters. So I have sum over clusters that are attached at V, so to say, okay? Now I take everything in absolute values, and this can be bounded by something. This something here in this particular setting is minus logarithm 1 minus RV, where RV is this number. Remember that RV belongs to interval 0, 1. So 1 minus RV is a number smaller than 1. Okay? Proof. I have 10 minutes for that, but it will be even quicker. Again, by induction in L. Okay? Only, I arose it, but somehow, so let me write it again. So there was this condition double I. First condition was easy. First condition was that ZL is different from 0, and this is satisfied. Okay, second condition is that sum over X in X such that support of X contains a given vertex V of what? Of absolute value AX, absolute value of W to the power X is smaller or equal than minus logarithm 1 minus RV. Okay, this was the condition 2. When I'm saying I'm going to prove it by induction in L, let me prove this, where I will call condition 2 with index L, will be the condition where this will be replaced by XL. I will take only multi-indices with support in L. Okay? If I prove this for every L, then I'm proving this also for infinitely large L. Okay, so again by induction in L. Again, I am even not bothering writing the first term because with empty or with 1 point set, it's trivial. Everything is clear. So we go immediately to the induction. And again, I use the same formula as before. ZL bar equals ZL times 1 plus W ZL minus NV over ZL. Okay? So now I want to prove what is first task. I want to prove that ZL bar is different from 0. I know that ZL is different from 0, so the only thing is that I need to prove that this guy here is different from 0. So let me take it in absolute values. So we know from induction that this is already different from 0. Let me take absolute value of the second term, and I want to bound it from below, eventually by something positive, okay? So I start, this is certainly bigger or equal than 1 minus absolute value of this, exponential of, and everywhere I put absolute values. This is certainly, again, I used my expansion already, which I know from induction hypothesis on, all these guys are smaller than L, are subsets of L, so there I know that my expansion works. I use this, I plug it into this ratio, and I'm getting this. Okay, you agree? Okay, I make it, as big as possible, so I'm putting absolute value everywhere. because I have minus here. So, making this as big as possible, I make 1 minus this as small as possible. Okay? So here the sum, I should specify over what is the sum here. Here the sum is sum over all multi-indices in L, such that support of this multi-index is touching NV. Yes? There was this complicated condition I wrote before. It was sum over all multi-indices in L, such that they were not fully contained in complement of NV. So it means that there must be at least one vertex in NV in the support of that, okay? Now this thing, I mean this sum with this thing can be estimated using this condition here. Here I have condition sum over all x's such that support contains a given guy. Here I am saying sum over all those guys such that support of x intersects NV. So it's clear that iterating this, I can get a bound that looks like that this sum here is bounded by, I was too quick, so it's bounded by, I have to write it somewhere, it's bounded by sum over v prime in NV, and then the thing I have over there, minus logarithm 1 minus RV prime. Okay? Because each, I am bounding this sum by saying any x should intersect NV, so it should intersect some point from NV, let me call it V prime. And going over V primes, I will certainly cover all this. So I have sum over V prime in NV, okay? And sum over x's that contain this particle V prime is bounded by minus logarithm 1 minus RV prime. So this is exactly what I wrote here. So this is exactly what is written here. I plugged it here, and what I'm getting, okay, I am getting this. So this is by iteration of this condition over there. So I'm getting what? 1 minus W, this is bound for this sum upstairs, this minus logarithm. So I have e to minus logarithm, so it is product, e to minus this sum. So it is simply product, this guy over V prime in NV, of this guy to the power minus 1. Okay? Everybody agrees? And this is exactly my star condition, which was so strangely looking, because, WV is smaller than RV. This is in my multi-disk, okay? And RV is smaller than this guy here. So if I multiply RV times this product times the product to minus 1, so the products will cancel, and I have 1 minus RV. And since RV is smaller than 1, 1 minus RV is strictly bigger than 0. Okay? And I am done and happy. Okay, so I know that ZL bar is different from 0. And the last step is I have to extend the validity of this guy to L bar. Okay? But this is quasi-immediate. Okay? Because I write some, there are these absolute values, and we know already that this is this minus logarithm, so the sum over all those that contain this V is exactly the ratio of L bar over L. I mean, e to this sum is the ratio. So if you start from the right-hand side, I made this computation. I was computing the ratio, z something divided by z something, and I wrote the formula. So exactly the same formula, then taking logarithm of this, I am getting that. Okay? And now I again, take out ZL of this, and I have minus logarithm 1 minus, and I write again this ZL bar star, I write as ZL star times 1 minus W times ZL minus NV divided by ZL. Yes? And this guy cancels this ZL star that will somehow come from this. They will cancel, and what remains is only this term as before. And now I was able already to bound, I mean, there should be a star here. I was able to bound this thing, to find an upper bound to I am upper bound to minus logarithm of this is the same as lower bound on this thing, and this was exactly the lower bound I was doing right now. And I was getting minus logarithm 1 minus RV. Okay? So that's all. So this is cluster expansion. Okay, and I'm afraid I'm done with my time, and tomorrow or after tomorrow I'm going to harvest from these nice formulas I somehow, I don't know the word now, I somehow thrown on you. I have thrown on you. I don't know whether it doesn't have nasty connotation, so I have some, okay. Yes?
Is this bound better than the old argument where you use the Cayley's theorem?
Which?
To bound the Mayer series?
Yes, it is better than anything else, in some sense. Not really, because there is a recent paper by. So this is equivalent to Dobrushin condition. Okay. There was this old Mayer series condition, then it was slightly improved in a paper we wrote with David Price. Then for many years this was somehow the best bound, and then it was somehow in this cluster expansion business there is Alan knows the story very well. There is this thing that everybody somehow dislikes how cluster expansion were done by the people before, and he proves his own theorem. Okay? So Roland Dobrushin even had at a congress in Marseille, he had a talk, he was not present, he was not allowed to go there, it was in 87, I believe, 86. So he was not there, but he had a talk presented by Michael Eisenman, and in this talk, the talk was remarkable by two things. First, in the title there was something without cluster expansion. Okay, so this was his ambition to prove something without cluster expansion. And then the second thing was that the important page number 10 was missing.
Oh, I thought it was the page with all the definitions.
Yes, we saw. So Michael was asked to present the talk, but he was presenting the talk from somehow from there were 10 pages, and an important page with definitions was missing. So he was somehow reconstructing what he could have thought or things like that. So this was then somehow so this was after our paper with David Price, but so somehow I was trying to convert Roland Dobrushin saying, look, I mean this is nice thing, and then we were writing the book about Wolf construction, and in this book we were using heavily cluster expansion. So then he somehow got converted, and then he of course didn't like how I was presenting it to him, and he invented his own presentation, and his own presentation was essentially what I was showing you, because there was this inductive thing, there was this Taylor expansion, and there was this condition, even written in somehow more horrible way, but there was this condition, okay? And this is the state of the art for this, so to say, discrete cluster expansions. And then somehow, very recently last year, there was a paper by Roberto Fernandez and Aldo Procaccia, who told me that he will not be here because he needs to do something. So they were able to extend it slightly farther, but with a method that I somehow.
You mean the disk of convergence?
Yeah, slightly farther. They have somehow they replaced this product here by some partition function living on these RVs. And what you have here, partition function on the volume NV, so to say.
But does this give you a larger disk of convergence?
Yeah, it gives you slightly larger.
You use the old method, like in constructive field theory, where you write explicitly the A as some over.
Yeah, I believe
I
that.
think the point is Dobrushin gives slightly better bounds than the old-fashioned
Right.
methods, but then Fernandez and Procacci used the old-fashioned methods with a trick to do what's sometimes better than the Brooch.
Yeah, exactly. So I do not like it terribly. I would like, somehow to rewrite their proof into this language, because then it would be really nice. But okay.
Could you just put up the proof of the last part of the proof?
Okay. If I will succeed.
Not that part. Yeah, this part.
Okay. I shouldn't go too far.
So here in this inequality.
So I believe I still can go 2 lines further.
Okay.
Here. Okay. So here we
So
have it.
that green inequality is a truncation of inclusion exclusion, essentially. You're doing inclusion exclusion on the set of multi-indices that intersect the neighborhood. And the first term is those that have 1 point in common with the neighborhood. Then you should subtract off those that have 2 points in common with the neighborhood. Add in those that have 3.
This is, this was the first thought I had when I saw their proof. I mean, somehow improving in their direction. I didn't succeed to push it through
But
somehow.
there's something called Bonferroni inequalities. If you truncate it after any odd number of steps, you get an inequality that's in the correct
Okay,
direction.
we should talk.
And I'm wondering if it reproduces the Fernandez.
Yeah. Because somehow, what they have partition function with these weights here somehow on NV. So only compatible pairs you take into account. And here you take everything. So product of all this. So somehow it's too big, clearly.
Yeah.
So you should replace only by this partition function, and somehow clearly I had the idea. I even asked I asked Neshetřil or somebody like that in Prague, and I didn't get any, so I believe that there must be something around inclusion exclusion. So, yeah.
So here, because if the neighborhood is very big, the number RV will be quite small. Because the product, if there are more times, when the value is smaller.
Yeah.
So I'm thinking whether it's possible to make a sequence of the vertices. I mean, your induction is putting vertices one by one. So is it possible to make this? So in the beginning, I don't need to consider all the neighborhood.
I don't know. I mean, you saw the proof. This
Because
is the proof.
your-
So somehow.
Your process of the proof is induction,
Yeah.
adding vertices one by one.
Yeah.
So in the beginning, actually, I don't need to consider vertices in the later vertices.
Yeah.
So I can make some.
Yeah, you can make some special, sequence of, you can
Yes.
somehow try to fill your space by a sequence of vertices
Yeah, if there
in
is
such a way that somehow it's well organized and you are
So
somehow,
to make some RV
yeah.
bigger.
Yeah, I can imagine that.
Another,
But somehow later on you will, these neighborhoods will be bigger and bigger
so
because,
how to control it, make a suitable ordering of the vertices.
yeah.
Another one is that, do you think it's necessary to consider two sequences, the capital RV and a small RV?
Well, not
I mean,
really. I
if
mean,
you
this is,
take
I just
a
can say that
Two-
absolute value of WV is
Yeah,
more than
my
this, yeah,
suggestion
somehow.
is that just the small RV.
Yeah, sure.
And the
This is
weightage
just-
of FVB is just consider the modulus is less than or equal to this function.
Yeah.
That's all.
Sure.
So don't need to
Sure.
consider capital.
Sure. This was, if you wish, this is just notation. I can say that RV equals this.
Yes.
Yeah. And
Well,
I simply
we don't
in my
define
polydisc
RV.
I didn't want to put index, which is this complicated
Yes.
animal here.
Because
I
it's
just
sometimes quite confusing, the two functions. How can we define two?
Yeah. But it's true that somehow you can, what is not totally clear to me, you can take supremum over all this.
Another one is that
Yeah.
we define when we prove this theorem, is it necessary, is really necessary to consider the log function, a log expansion or not? Or just go straight to prove it? Because for the real case, I find the proof is very simple. We don't need to go through the log function, the log expansion.
Well, but this is what I want to have.
Yeah,
This is my-
now you use the log function,
Yeah.
come back to prove it.
Yeah.
I mean, it's go straight.
You mean in the ratio like
Yeah.
that, to
Yes.
go somehow directly?
Yeah, go straight.
Yeah.
Don't need to use.
Yeah, but somehow since this is for me, log function is the end result, so I have it anyway.
Because
I
I
have-
find for the real case, it's very simple.
Yeah.
But for the complex, I still haven't finished the proof.
Yeah.
I try to find a simple proof.
Yeah, yeah. Okay, so all this sounds very interesting and exciting.
Yeah, because for a real case, we can save a lot of energy from here because we don't consider the positive case.
Yeah, 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 yeah. Yeah, sure.
Is this an infinite product?
Yeah.
So can you say something about the existence of this RV?
Okay. I do not remember, unfortunately, so this is, I deliberately didn't start to tell anything about that, but I believe that the correct choice for my model with the weights that equals e to minus 2 beta gamma. So I take r of gamma equals, I believe that something like that, e to minus 2 beta gamma. Essentially, you know, I have to check. Maybe all this minus 1 or something. I don't know, something like that. And maybe there is plus somewhere on the way, you know. Maybe it is e to plus, e to minus 1. Yeah, it's almost surely this. But you know, I do not remember and I didn't find it here, so I have to.
Are you saying there is a general, this R always exists, or you saying
Yeah,
just in this example?
No, in the examples where you know, I mean, somehow the standard application is that I know the W gamma is smaller. The gamma is really some contour or something like that, and W gamma is smaller than e to minus some tau of gamma or something like that. This was both our examples. I had either e to minus 2 beta gamma or I had tangents hyperbolicus beta to the power gamma. So I had always, you know, something, or I can write it epsilon to the power gamma. Okay, so always I have something like that in applications. So I should be able somehow now to tell you what for this application, which I know that everything goes through, what is RV, and I believe it is this.
Thank you.
Yeah, and this I will start with Thursday somehow showing applications. So in particular, this will be the
I
same.
think we could restate the theorem so that it make it more natural. Just consider any RV, the small RV.
Yeah.
And as long as the small RV is less than 1, between 0 and 1. No, between 0 and 1.
Well, you need really, you know, it's really somehow, you know, in terms of this RV, I know in terms of the thing we were doing with David Price.
It's always true.
But
as long
it's
as the RV is between 0 and 1.
Yeah, yeah.
And the capital RV is defined by this, less than this.
Yeah.
And the theorem works.
Yeah.
So, I mean, such a way is more natural for writing this theorem.
Yeah, but okay, this is what is here. Simply, this is definition if you
Yes,
want,
correct.
and this is the thing. But somehow it's not enough that the product. You know, I really need this. I need both sides. So you know, RV or W must be smaller than, you know, R times the product of all the guys. You know, all the neighboring guys. So there is this double somehow. Okay, you wanted to ask.
I was just throwing an idea. Did anyone try a method kind of like renormalization group where you would define another system with effective W's and like to try to extend the radius of convergence, like to prove convergence on a big thing, you find it effective.
Yeah.
Which is a smaller, which falls in the radius.
Yeah. I am not really aware. What I am aware of and what I would like to try to work at is that somehow what people are doing. If you have some random something, you have random Ising model with some random interaction or something, not really spin glass, but say, you know, random dilution or something like that. And then you may have random ferromagnetic interaction. Sometimes it's big, sometimes it's small, okay? And if it is small, this is bad region for cluster expansion somehow, okay? But in the mean, if you somehow do some renormalization, you can somehow forget about that. So there are papers by Olivieri and people around him who are doing something like that for these random systems, but they are doing it in quite cumbersome way, and I somehow believe that it should be, using this language, it should be possible somehow to improve that, but I still didn't, you know, seriously think about it. Yeah?
Ask about the question we had earlier about deleting and contracting vertices. So I guess deleting vertices in this graph is just deleting the vertex, and contracting the vertex is deleting the vertex and its net descent. Is that the two operations?
Well, I'm contracting. I'm deleting. Well, this minus NV is exactly what you called minus V.
Yeah, but
Yeah.
there was a question earlier that
Yeah.
what you were actually doing was deletion and contraction of vertices. So the contraction,
Yeah.
so the other operation you were doing was you were deleting a vertex and its neighbor set. So I guess that's what he was thinking of as
Yeah.
contraction.
Well, I answered to his question that I didn't quite understand what he said. So. Okay. So.
May be that deleting could be thought of as considering those terms for sets that don't contain the vertex, those independent sets that don't contain the vertex, and contracting would be to consider all the independent sets that do contain the vertex.
Yeah.
And as such, none of the neighbors can be in such an independent set in the second case.
Yeah. Okay. Thank you.